uh, template metaprogramming. So last time we have discussed how to detect inheritance relationship by using some of the techniques of template metaprogramming. In particular, we have seen this neat trick of defining two different data with two different sizes to have functions which are not implemented that take different kinds of arguments and return different kind of data, and then use this in a size of expression to understand if the conversion is possible or not. And it works very nicely, and we can actually detect if a type is a base class for another type or not. We have seen also other kind of tricks like how to transform an integer into a different type so that we can do template specialization or overloading of functions, so that we can select one function or the other depending on something we know at compilation time. So these are a lot of very nice tricks. Another trick I would like to show you, this is not very important actually. It's something that is not used anymore because now the C++ standard defines variadic templates. But in the past, before variadic templates, this trick allowed you to define a list of templates. Let's see how it works. So a type list is a list of types. So as a normal list is a list of objects, a type list is a list of types. A list of types is another type and has no specific size in memory. I mean, it's a sort of empty structure, much like a structure like this. Let's see if I find it again. Like this, right? So this is an example of structure which basically has no real implementation in at runtime, except the fact that these types exist, and so it takes just one character in memory, so 1 byte. And the same is for type list. So a type list is not something that exists in memory, but something that exists for the compiler, so the compiler can do computation with that. So here is, for example, a type that is called null type. Again, its size is 1 character, and we are not going to instantiate it because we don't really need to have variables of type null type. However, null type is used because the compiler needs to make type comparison. So we define an empty type that we call null type, which will act as a terminator for the list of types. And then a list of type is something like this. Is a template with two parameters. The first one is the head of the list. The second one is the tail of the list. So the head of the list is going to be another type, and the tail is going to be either null type or another list. So we recursively define a list of types in this very, very simple way. Of course, we cannot do very much with this list of types right now. So we are going to define meta functions, that means things that act at compilation time for manipulating the list of types. So again, this is template metaprogramming. So all the things we are going to discuss right now happen at compilation time and not at runtime. So let's see a few examples. I'm going to have a list of two types, int and double. How do I define this? This is a list where the head is going to be integer, and the tail is going to be another list where the head is double and the tail is null because there is nothing else. So this is a list, a type list with two types, int and double. And I can define another type list with three types, int, double, and char, and it's going to be a type list in which we have int in the head, and in the tail is another type list which has double in the head, and as a tail has another type list with char and null type. So it's a recursive, one inside the other, a recursive definition of type list. Sorry, just 1 second. I'm going to check. Yes. Okay, so you have this recursive definition of type list. It's very difficult to write these kind of things because you have to type a lot. It's not very nice to type all these things. So how can we simplify typing a little bit? Well, we can define some macros. For example, a type list with one single type inside is just a type list with T1 and null type. And the type list of two types is just a type list with T1 and type list 1 of T2, and so on. So we can define a lot of these macros, and then when we want a type list with three types, we just write type list 3 int double char. Okay? Now remember, the size of variable int double char is 1. Okay, because it has nothing in memory. This is just a list of types that is used by the compiler. So a type list is not a useful class because it does not contain code. It only useful to help the compiler generating new code. So it's a trick to pass types instead of values to another template. So, for example, a type list can be used to obtain the various types in the list. So, if I want the first type, I just write 3 types head. And if I want the second one, I have to write 3 types tail, head. And the third type is 3 types tail, tail, head. Now, it's quite ugly, but it works. Because I defined the 3 variables of the right type. Okay, now suppose I need to write the code for a structure that must contain 3 data members, but I do not know a priori the type of these members. I would like to write generic template code that instantiates the structure with the right types. So I want a structure which is passed a type list, and then the first parameter is the first element in the type list. The second parameter is the second element in the type list, and so on. So I want something like this. My structure type list 3 int double char s, and then this defines parameters 1 as 5, parameters 2 is a double as 0.75, and the third parameter is a character. Okay. Okay, so I can simplify type extraction by using a few meta programming tricks. For example, I can define a function, meta template function, which is a structure type head. Type head takes a head, a tail, and an index. And typically it does a recursion in the sense that type head is just type head of head, type tail, and index -1 result. And if I want to specialize for 0, I have to write this, and of course I just get the head. So the idea here is that normally if I write like type head or head tail I, the first one is executed unless I is 0, and then this one is executed. Okay, And then if it reaches the end of the list with index greater than 0, because there is a null type in T, then a null type is the result, because there is nothing after that. So this is index 0, I get the result. This is the special case in which index is greater than 0, but I reached the end of the list, and this is the special case in which I just got the last element. In this case, H is the result. So now I can write things like L is the type list, my structure. Type hat L0 is parameter 1. Type hat L1 is parameter 2. Type hat L2 is parameter 3. And so I can write exactly like before, but I can avoid the ugly definitions like this. Okay? So this is a template metaprogramming. I'm programming a structure dynamically depending on a list of types, like that. So this is a template meta function, and this is a template meta structure because I just defining that programmatively by writing like that. Okay, then we can define other functions, like for example auto compute the number of elements in the type list. And again, I write a structure that works in general. Then I write a structure that works when I have a null type as a second element. And then I write a specialization when I have something different from the null type as element. Okay, so this is how it works. Okay, but in general, this is very nice tricks, but they are not so much used anymore because in the new standard in C++11, they decided to make it easier for programmers to use this kind of tricks by embedding these kind of things in the language. And in fact, the new standard provides compiler support for type list by introducing the concept of variadic templates. So a variadic template is a template with a variable number of arguments. And if I want to know how many arguments has been passed to the template, I can write this specific syntax here means count the number of template arguments. Specific syntax here, type name dot dot dot, means that the number of arguments is actually variable. So I can pass a variable number of template arguments. Now, using these kind of things is not very easy. So we are going to directly see an example. And the example is about using writing a more evoluted printf. So the fact is that in C++ you do the output by using cout. Now cout is nice, but also a little bit not very easy, because when you have to write a lot of parameters one after the other, you have to repeat the cout several times. So the syntax of using cout is not incredibly nice. Printf is a little bit better. The problem with printf is that the printf is not size. You have to write percentage %d if you want to print an integer, percentage %s if you want to write to print a string, and there is no check at compilation time that the types are matching. For example, one could write something like this. So what happens here is that the printf expects an integer, but actually I'm passing a character. Now most modern C compiler will catch that. They are smart enough to look inside the string. But that's not always possible, because sometimes, for example, the string is built by the program in some strange way. So it's not possible in general to do this kind of check. Also, it would be nice to have something like this, in which the type is automatically derived from the type of the argument. Okay, so why don't we write in C++ a safe printf like this? Allows us to write any type of argument and with a variable number of arguments. So I can print an integer, a double, and a string like that. So how can we do that? Well, we can write that using variadic templates. So let's see how it works. So we are going to write two definitions of a function safe fprintf. The first one is not a template. It takes a host stream on which we want to print, it's going to be cout in most cases, and it takes a pointer to a sequence of characters. Then we are going to, so this one is the case in which we don't have to print any argument. So it's exactly this case, the second one. Okay, so we don't have anything to any parameter to print here. We just have a string of characters. So we want to print it one after the other. So we do this while s is different from 0. So while we are not at the end of the string, we check if we have a percentage character and if the next one is again a percentage, then it means we really want to print a percentage character. So we just increment s and then later on print it. Else, if we have a percentage character which is not followed by another percentage character, then we throw an exception, invalid format string, and missing arguments, because it means that we have written something like this. This means there was a parameter, but I don't see any parameter, so I throw an exception. Okay? So this is the base of the recursion we are going to implement. The case in which we don't have any argument following the specification of the string. Now let's suppose we have a certain number of arguments following the string. So after s, we have a certain number of arguments. And the first one is going to be t, and then we have a sequence of arguments. So we do the same. While s is different from 0, we continue iterating. If we find a percentage and the next one is again a percentage, then just we increment s and we are going to print as before. If instead we find a percentage and the next one is not a percentage, then we print the value and then we invoke again the safe printf by passing the remaining arguments s plus 1 and out. And when we finish, we return. So this means that we processed this argument and then we call safe printf by passing the remaining. Now, if args is nothing because there are no more arguments, this is going to call the base of the recursion. Otherwise, is going to call again this function, but with a different type of argument t and with a different argument list here. So this is the recursion. Okay. Of course, if we are in this function and we are out of characters in the string, but we still have t to process, then we throw an exception, extra arguments provided to print. That means, for example, that here we are calling the function like that. So if the number of percentage doesn't match the number of arguments, we throw an exception. If they match, everything works okay, and we are going to recursively invoke those functions. Actually, those are different functions, so it's not really a recursion of the term, because we are not calling exactly the same function, but a different function, because the template. And finally, I'm going to write a shortcut when we want to print on the standard output, like this. So, for example, I could write save. Sorry, what kind of error did I do? That was not declared, yes, because I have to write like this. Okay, so this is an example, and I'm printing on error stream. Okay. So variadic templates. You find also pretty much the same thing here, taken from Wikipedia. Another thing that is based on variadic templates are tuples, and tuples are defined again in the standard template library. So, for example, instead of using those type lists we explained before, we are going to use a tuple, which is already defined before. And a tuple is a structure which contains an integer, a string, and a vector of integers. And you can access the first, like this, standard get 0, 42. So this is going to access the first parameter of this tuple, which is an integer. The second parameter is going to be my name, and the third parameter is a vector over integers. Okay, and of course you can print, you can do whatever you want. You can assign, you can print, you can do whatever you want. Here I missed the parentheses, sorry. Okay, so variadic templates and list of types. Let's see what else. I'm going to explain now a technique which is called curiously recursive template pattern. It's another nice pattern that can be used sometimes. And in particular, it's useful when you cannot use virtual functions in your program for some reason, and you want to have something that looks a little bit like a virtual function. So the basic pattern consists in a base class that has the derived class as template parameter. So it's a very simple pattern. You have a base class, which is a template with a parameter x, and then you have a derived class which derives from base derived. So it's curious because base uses as template pattern the class you are just defining. So curiously recursive template pattern. How this can be used? Well, for example, one use is that you may want to define counters for how many objects or a certain class you are going to have. Suppose that you want to count how many objects have been created of a certain type. So what you can do is to define a class counter which has a static integer counter and then an integer index. Every time you create an element of class counter, you increment the counter and you assign the value to index. And when you want to know how many have been created, you just call function how many, which is a static function which returns a counter. Later on, if you want your class to have this functionality, you can derive from counter and know how many of these there are. If you do this naturally, unfortunately, you are going to have one single counter for all classes that want to use this technique. So if I use this technique like this, what I have is that since all these classes derive from one single class counter, you see, since all these classes derive from one single class counter, there is only one static counter for all of them. So every time I create an object of type A, and then I create an object of type B, and then I create an object of type C, and I write well, the response here is going to be C is going to print 3 because I have 3 objects of type counter around, right? So this is not very nice because I actually would like to have 3 separate counters for every class. However, that's not simple to achieve normally because I need several counter classes with several different counters for each. And I cannot make this non-static because if I make this non-static, then it doesn't work anymore. There is no global counter anymore. So I would like to have separate counters for separate classes. Now the solution is simple. I make this a template class. And as you can see, X is not really used inside counter. Because counter classes around. The first one derives from counter A, the second one derives from counter B, and the third derives from C. So if I write how many, this is going to now print 1. Okay? So I have this nice property that I multiplicated the number of counter classes for every class. Let's see if it really works and compiles. So sorry, I did a mistake here. No, cannot do that. Sorry. Yes, I have the problem of initializing, so I'm going to do. Oh, I still have this, sorry. Work finally. Almost. Okay, finally. So this prints 1 as it's supposed to be, while if they all derive from 1, then it's not going to work. So, for example, okay, so, but you understand, I guess. So this is one application of the, it's a very simple application of the curiously recurring template pattern. Another application is to simulate the use of virtual functions. And the idea is that you have a base class that performs a cast to derived classes before invoking a function. So in this way, we can call the overloaded function in the derived classes from a base class function. And this is quite similar to what happens with virtual functions. So suppose, for example, you have this structure in which you have a base class which has three functions, f, g, and h, and each one calls the corresponding implementation. And of this implementation, the first two are virtual, and the last one is non-virtual. Okay? And then you have a derived class, which derives from base, in which you redefine the implementation of f and the implementation of h. And remember, the first one is virtual, the second one is not virtual. So later on in the main, you have x as an object of type derived, and you call f. So you call f, you go up, and you see that f calls imp f, which is a virtual function. Now, since the object is of type derived, this function is going to be called. So the first one will call derived imp function. Okay? Then suppose you have x.g is called. Internally, this will call implementation g. There is only one implementation g in base, and so this will call implementation g in base. And finally, suppose that you call x.h. This will call h, which in turns wants to invoke the implementation. There are two implementations, but since h is not virtual, the implementation H of class base is going to be called. Okay, so this is a classic virtual function calls, right? How can we simulate this without using virtual functions? So we are going to, for this, we are going to use the curiously recursive template pattern. So we have base, which is now a template class. F first performs a static cast to T of these. So this is first cast to T star, and then implementation F is called. And the same for G, first static cast to of this to T star, and then implementation G is called. And finally, H just calls implementation H. Then you have the three implementations here. And in derived, you have you redefine the implementation for F, and you redefine the implementation for H. Now, X calls F. So derived is a public base derived. So the template parameter TER is actually derived. So XF first takes this and performs a static cast to derived, and then calls implementation F. So calls derived implementation F. And X.G calls implementation G. This performs a static cast to derived and then calls implementation G. But there is only one implementation G here, so it invokes this base implementation G. And finally, X.H calls implementation H, and since there is no virtual anything here, this implementation H is going to be called. So, incredibly, we are replicated the behavior that was achieved here with virtual function. We replicated, and now we are using just a template and without any virtualization. And so basically here there is no virtual table involved anywhere, and there is not the overhead of the double forwarding of the virtual function call. And this means also that probably the compiler has some way of optimizing it. For example, in embedded system, it's sometimes necessary to not use virtual functions at all. So in that case, you can use this technique for simulating the virtual function call. So I have implemented this. So we look at virtual. So this is the implementation by using virtual functions. Then I have the sim virtual, which is the implementation using the pattern. And of course, if you are going to execute this, virtual will print derived implementation F, base implementation G, and base implementation H. And if you run sim virtual, you obtain exactly the same thing. Of course, virtual functions cannot be entirely substituted, because in the previous example, the binding is always static, because it's always made by the compiler. If you really need a real dynamic binding, you cannot escape virtual functions. So you cannot entirely substitute virtual functions. For example, if you have a derived A x, derived b y, and then you have base ampersand r equal to 1 between x and y, then r.f needs a dynamic binding to understand which one is going to be called. And there is no way to use the curiously recurring template pattern to simulate this behavior. So if you are going to call virtual functions by using pointers to the base, you cannot, of course, use the curiously recurring template pattern. So you can use the curiously recurring template pattern only when you have a structure like this, derived, which derives from base, and the object derive, you access the object derive by using static functions that internally redirect towards virtual functions. This thing, so you cannot use this. So where you want to use this technique can be used in an embedded system where we may actually know all objects at compile time. So the dynamic binding is probably not really necessary. You want to avoid the overhead of runtime type identification and dynamic binding because it brings some overhead with it. But you still want to be flexible in using inheritance and the ability to choose the implementation at a later stage without needing to rewrite the program. So it combines, let's say, the flexibility of using a hierarchy of classes with avoiding the overhead of runtime type identification. And finally, one last way of using this technique is in avoiding, for example, rewriting the functions which are very common from one class to the other. Suppose you have your usual hierarchy of shape, and then from shape you derive squares, circles, and so on. And suppose this is a polymorphic hierarchy, so you are going to copy elements by using a clone function. Now, when you do this, you have to write one clone per each derived class, because in the clone you have to do the new with the actual type. Now, this is a little bit annoying because you continue to repeat the same code everywhere. So if you want to avoid it, you can use an intermediate class, which you call shape CRTP, which derives from shape, but it also templatized with respect to the derived class. And you implement the clone once and for all by creating an object of type derived and passing this as an element. Okay? And of course, you have to static cast this to derived, otherwise it doesn't work. No? So basically, this is going to invoke the internal copy constructor, and which you have to write for the derived classes, and the clone will just new the copy constructor and return the new point. And now in the derived classes, you just write directly the fact the square derives from shape CRTP of square instead of directly deriving from shape. So you have one intermediate class in the hierarchy, which is called shape CRTP of derived, and all the classes deriving from this shape TRP already implement the clone for you. Okay, we do a 10 minutes break now, and then we continue with a little bit more of template metaprogramming. Let's have a break.
Yep. Devo farle una domanda su i variati template. Ha fatto vedere come si possono accedere oltre che nel modo ricorsivo. E lei ha fatto vedere che
no, si possono accedere solo nel modo ricorsivo.
Solo nel modo ricorsivo.
Non c'è altro modo. È tutto insieme o nel modo ricorsivo?
Scusi, volevo chiederle una cosa sui parametri del compilatore. Come si fa a vedere il codice C++ generato dopo il parsing dei template, cioè lo sviluppo dei template? Cioè si può? Ce l'aveva fatto vedere lei?
No, dei template no.
Ah, dei template no?
No, no, si può fare delle macro ma non dei template, almeno che io sappia, dipende probabilmente dal compilatore, però di solito non viene generato il codice C++ dei template, fai la parte che poi viene compilato, no.
No, no, dico, magari non viene generato, però magari c'è un flag che gli dice mostramelo, no, non c'è.
Non mi risulta, può darsi pure che qualche compilatore lo faccia, però io GCC mi sembra proprio di no.
Sì, infatti male la comunità.
Okay. Let's start again. Among the examples that you find in the code for this lecture, there is also an example with the tuples. So here is how to use one example using tuples. There is the use that I use for my examples, and then in main I prepare a tuple like this, auto t. Then I use a function make tuple, and the tuple is going to have a pair of two strings, then a string, and then an object of type myClass. And the first object is a pair of Douglas Adams, and the second one is the title of his famous book, and the fourth one is 42. And then with the get 1, get 0 first and get 0 second, and then get 2. Okay? And as you can see, get actually returns an object of the correct, so then you can apply it the internal things. So this is solved by the compiler, as I said. So this is a way to generate code. And that's why this works, because the compiler, when compiling this code, it knows that this type is a pair. And so it knows that as a field first and a field second. Okay, so it's not something dynamic that is going on here. Everything is statically compiled by the compiler. So again, these template metaprogramming techniques, like meta, blah, 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 are all ways to generate code with a few lines of code. So you write a few things and it generates the code. In particular, in this case, you didn't need to write a structure, I don't know, a my tuple. It's the old, okay, and so on. That is the old way. Here you should have done auto t equal my tuple, and then you should have initialized every single member. Then here you should have written parameter 1, parameter 2, parameter 3. You don't need to do that because you don't need to define your own structure, as you can do that statically, like this. Okay, it's maybe not very useful. Maybe you will never use things like that, but it's nice to know these techniques, because you may actually encounter this kind of techniques in somebody else's code. Actually, also one thing that may be useful is to understand the policy technique. So how to structure the code in a policy structured way. So suppose you have a class and you want to customize the class with a specific policy that can be one thing or another thing. For example, one algorithm for sorting or another algorithm for sorting. Or, like in the case of the vector, one algorithm for allocating memory or another one. So depending on which kind of things you have to do, you want to customize your own type with different strategies. Okay. Typically, the object-oriented way of doing that is to have one class one type int, which provides you the function that implements the strategy, and then you are going to implement the strategy in different ways with different. Apply this strategy to the class you want to implement. The meta template technique for doing this is of a strategy-based class. So you're going to use S, which is the strategy, as a base class. And you are going to derive privately from your strategy. And inside here, then, you use the operation you want to use, which is going to be okay? And in the main, you customize your composition with a certain strategy. Okay? So this is called policy-based design. Has been proposed for the first time by Andrei Alexandrescu, and it can be used because it's actually quite useful. So how to customize a class by using one strategy or the other. Okay. What if you want to use many strategies? What if you want to customize your class with an arbitrary number of strategies? Well, in that case, it may be useful to use sorry, yeah, it may be useful to use variadic templates like this. here. This means basically that the class is going to derive from many base classes. In this case, publicly, but it could also be privately. And when you initialize your class with the constructor, you are going to initialize all the base classes like this. So this is the syntax for having a class which derives from many classes, and a priori you don't know from how many. Okay, so you are going to add new policies here in the interface like that. Okay, so if you are interested in template metaprogramming, actually the new standard, C++11 standard, provides you with many helpers. For example, this is so these are contained in type traits. Type traits contains many of these helpers. First of all, it contains a few structure that allows you to check the type that is passed as a template parameter. For example, suppose we want to know if a type is a pointer type. Well, we can use this template metaprogramming function, which is actually a structure, as you should have already understood, and you pass one type, and it's going to provide an internal Boolean value, which can be true or false, depending on the fact that t is a pointer or is not a pointer. So by checking this value, you can know at compilation time if one particular type is a pointer or not. So when you write your template function and you want to make sure that your type is a pointer, you can check this point. Or I don't know, you want to know if an object is polymorphic or not. Okay, so if that's virtual functions or not. And so this is going to check if it is polymorphic or not. If he has a default constructor, if it has a copy constructor, if it has a move constructor, if it has an assignment operator, and so on. And if two types are the same, if one is base of the other. We have already seen all this last lecture, and this is already implemented in the standard. Okay, so you have all these nice helpers for you. And also you have things like conditional, which in my slides was called the select. Basically is a template with three parameters. The first one is a Boolean, and then we have true or false classes. So basically this provides a member type def called type, which is defined as t if b is true, a compile time, or as f is t is false. So here you have an example. Type def standard conditional true int double. So this type 1 is going to be int, and this one type 2 instead is going to be double, and this type 3 is going to be int is greater or equal to double. Well, on a 64-bit probably yes. So this is going to be int, or maybe a 32-bit no. So this is going to be double. So depending on where you are, you can have different assignment for int or double. Another one is enable if. It allows to use what we called the last time the sFinae. That means substitution failure is not an error, and so this is a technique for allowing to have to select the correct overdot resolution. So let's see if there is an example here. Yes. So this allows you to select a function foo1 for integers or for floating point, depending on the type of parameter t. So basically, if you go in the main, if you call foo1.to, this is going to call the first version of foo, because it's a floating point. Otherwise, foo10 is going to call the second version, which is the integral version. Okay? So depending on which one, you have enable if of one type or enable if of the other type. Okay. What else? Another nice thing I found on Stack Overflow is this technique for variadic templates. Basically, here he wrote a sort of a template meta function for finding the largest type from a group of types. So he started by defining this. When you have one single type, then find biggest, of course, puts first type. And if you have many things, then you first find the biggest and you put that into next. And then conditional. If the size of first is greater than the size of next, then first. Else, next. And then type is going finally to be the type you need. So this is a sort of recursively templated function which is going to put into type the type with the largest size. Okay, so maybe this is just an example, it's not very useful, but it tells you how to use this template metaprogramming. Before going to explain the last metaprogramming technique, I would like also to show you a little bit of functional programming in C++, because sometimes all these techniques are mixed together to achieve one certain result. So functional programming, it's a movement, I would say, of programming languages that where the emphasis is on using pure functions as much as it's possible. There are languages based on functional programming. The most famous is Haskell, but also you will find many other languages. For example, there is a modification of Java. I don't remember the name right now, but there is one evolution of Java which is functional programming. And so the emphasis of these languages is on using pure functions. So a function is pure if it has no side effects. So basically, the idea is that when you give the function a set of values for the parameters, the result is going to be always the same. And there is no side effect. So for example, all mathematical functions are pure functions. But also, if you are going to sort a vector, sorting the same vector always gives the same result. Or when you compute the determinant of a matrix, and so on. In general, using pure function is desirable because, first of all, they have no internal state. So maybe sometimes they are easy to understand and to code than complex functions which modify the state. And second, they are desirable because in most of the cases they can be executed in parallel. because they use no shared memory. Every function acts on the parameter separately in read mode without modifying anything. It internally uses local functions, so they are in different portions of memory, and so they do not interact. So if you call the same function from different threads, you are not going to have any interaction, and so everything is going to work. So in general, for parallel programming, it's better to structure your code using functional programming. Now, functional programming is actually quite the opposite as object-oriented programming, because the idea in object-oriented programming is that you have objects that contains variables, and variable means state. And then you modify the state by using member functions. So in object-oriented programming, the emphasis is on hiding the state behind an interface and using the interface for modifying the state. The emphasis of functional programming instead is in not using at all any state, but just using functions that compute partial results and combining this partial result to obtain the final result. So the final result is, consists of applying functions one after the other to an initial input. In object-oriented programming, instead, you have objects and you modify the state of these objects in a certain sequence to obtain the final result. So the emphasis is quite different. Again, in object-oriented programming, you take the state and you hide it behind an interface. In functional programming, instead, you try to avoid any state entirely. So, very, very, very simple example. Suppose you want to sum all elements of a container in C++. For example, a vector. Typically, the C-like way of doing it is you define a variable S, then you go through the vector and you sum all the elements into S. And then you print the sum. So here is non-functional because we are using a variable, S. The variable is a state. The state is modified inside a loop. Okay? In non-functional instead programming, there is no state at all, and nothing is modified. You have a vector, okay, I'm not going to touch the elements of your vector. The only thing I do is I call a function that I call compute sum, and this function is a recursive function. So there is no state anywhere here, and also there is no loop. The loop is implemented by using a recursion. So here I'm going to do, sorry, there is some typo here. So I'm going through the elements of a vector. How? If b is equal to e, I return 0, because the sum of no element is 0. Otherwise, I return the content of b plus the sum of the elements after b until a. Okay? Actually, here I should not do plus plus b. I was wrong. I should do b plus 1. So I should not modify b, actually. Okay? Actually, this is actually also undefined. So I did a big error, sorry. So this should be written like this, sorry. Okay? So now it's correct and it's functional programming. Before it was not. Actually, before it was a very bad mistake. Anybody knows why this is a bad mistake? Does anybody knows why this is a bad mistake? while I'm writing. Had we found the solution? Solution? Why this is a mistake?
Depend of the type of the template.
Depends on?
The type of IT.
No, it doesn't depend on the type. So, the error is here. Why this is an error?
Maybe because the compiler can reorder the sum.
Exactly. So this is called undefined behavior. Undefined behavior means that the behavior, the output of this program is not deterministic. It depends on the compiler. It depends on many things. It may also depend on the processor in certain cases. Why? Because the actual evaluation of the different elements of this expression, it doesn't happen in a specific order. So it can happen that the compiler decides to first increment b, then compute the sum, and then take the element pointed by b. Or it can decide to take the element computed by b and then compute increment b and compute the sum. We don't know which one the compiler is going to choose. So depending on some choice which we have no control of, we have one behavior or the other. Let's hope the compiler decides for the best here. So in this case, everything is okay. The sum is 10. But as I said, this is not under our control. So this is a potential source of undefined behavior. And unfortunately, C++ is full of these tricks and of these very bad things. This version instead is okay, because it doesn't matter how I order the evaluation of the different parts of this expression, the result is always the same. So this is actually functional in the sense that it doesn't matter. So we get the same result, but that's by chance. We don't know. Actually, let me check if by changing the optimization level, maybe we get some different result. Okay, no, C++ is very stable in that. It always gives the same result. Okay, but anyway, don't do that. Don't use b in different parts of the expression with different by changing the state in one of them, because we don't know what is going to happen. So this is an undefined behavior. Okay, so going back, this is a functional sum because nowhere I'm modifying any state. There is no partial result anywhere, except then in the internal computation of this recursive sum. Okay? So this is a more functional version of this sum. Okay, so how do we program in a functional way in C++? Because C++ is not a functional program language, so it doesn't give us all the things that we need for functional programming. So how can we write functionally in C++? As I said, you can, of course, write in every single language. What you need to do is to understand what are the basic operations of functional programming. So the emphasis is on functions. So in functional programming, you have to actually manipulate functions. So you need to do, for example, treat a function as it were an object. So first class thing in the language. So you need to pass a function to another function, returning a function from another function, and so on. And we already know how to do that, for example, by using function objects. Okay? Function objects are a little bit like functions, but they can be treated as objects. Also, we would need to compose functions. For example, given f and g, we want to obtain another function which just is the composition between f and g. So you first apply g, and then the result you apply f. Or you may want to bind a parameter. For example, if you have a function that takes 3 arguments, you want to bind the last parameter to a certain value and obtain a new function that only acts on the first 2. So how are we going to do that in C++? Well, you can use what is defined in the functional header in the standard library. The first thing that the standard library provides you is a wrapper for any kind of function, and it's called, by the way, function. So you can wrap anything that looks even remotely as a function inside an object of type function. You have to specify, of course, in the template parameter, you have to specify the return type and a certain number of arguments. Now, instances of standard function can store, copy, and invoke any callable target. For example, a function, or a function that you can define on the fly by using lambda expressions, or a function that you obtained by binding some parameters of another functions, or a function object, or whatever. And you have something similar that is called memfn, which works for member functions or member data of any class. So it's a wrapper for members. Okay, let's see one example here. For example, this is how to wrap members of a class foo. You have a function display greeting, a function display number, and a data member data. And you can write auto greet standard mem function foo display greeting. Okay, so greet now is a function object, and you can call the function object greetf by passing the object on which you want to call the function object. In this case, what is going to happen is that it's going to print hello world. Then you can transform display number into a function f that takes an integer, takes an object and an integer, and you can access data of an object by transforming the access to this integer into a function access data. It takes an f, which is the object on which you are going to call the member function. And this instead is one way, for example, for you have a vector of strings, and you want to compute the length of every string. You prepare another vector of lengths, and then you apply transform on the begin end of words. We are going to put the result into lengths, so standard back inserted lengths, and on each element of the initial sequence words, you are going to apply standard string size. So at the end, length will contain the length of all the strings. Okay, so this is a typical functional approach to solving a very simple problem like computing. Of course, we are more customized with using the standard for cycle, right? I mean, if you have to do this, you would write a for cycle which just prints all the lengths of every single word in vector. Here, instead of using the for cycle, we just compose functions. Transform applies these functions to all the member of the first vector and produces elements to insert in the second vector. And then you have this string size transformed into a normal function that you can apply to objects. You can also bind arguments by using bind, and the idea is that you can basically it takes a function and some arguments and binds some of these arguments, obtaining a new function. Okay. Let's see how it works with a few examples. For example, suppose we have a function f which takes an integer and a double. And for some reason, you need to swap these two, in the sense that you need to pass this f to somewhere else, in which the call happens by passing first a double and then an integer. Okay, how can you do that? So f usually is called by passing an integer and a double. And suppose we want to call it doing the other way around, passing first the double and the integer. Okay, so you write this. Standard bind f underscore 2 underscore 1. Underscore 2 underscore 1 means the original second, the second argument of f order goes in the first argument of f. And the first argument of f order goes into the second argument of f. So now when I call f order y x, what happens is that this f is called by passing an integer and double in the right order. Or suppose another example, maybe a little bit simpler. Suppose you have a structure which has a function print sum, which prints the sum of the two integers, and then you have a member data of type integer. Then you define an object foo, and then you define a function f3, which takes this function print sum, binds the object foo, binds the first argument 95, and leaves one single argument. So function f3 now has one single argument, which is passed as a second parameter in print sum on object foo, and the first argument is always going to be 95. So whenever I call f35, the function print sum on object foo with first parameter 95 and second parameter 5 is called. And I can do something very similar also to data. So data is seen as a function which just returns the value. So I can do standard bind foo data and underscore 1, which is basically the object. And so basically I can write f4 foo. This is going to call a function which returns the value of data on object foo. So I can do very, very strange and nice things. Okay, so before going to expression templates, I thought we could finish today, but unfortunately there was not enough time. So we will continue tomorrow, and we will continue a little bit by looking at examples with these functions, and then we are going to look at expression templates. So sorry, it's not the right one. So expression templates, which is a special pattern that is used in C++ for that combined with functional programming can give you very powerful things like, for example, here, A begin, A end, X, L plus X is going to evaluate this expression on the several elements of this sequence. So it's quite a nice way of writing expressions using C++. So, but we are going to look at that tomorrow. So for today, we stop here. If you have questions on the project, we are going to discuss on the project tomorrow. But if you have a specific question, please prepare so tomorrow we can have a discussion. So tomorrow we are going to have 1 hour about expression templates. In the second hour, we are going to discuss about the third project, the final project. Okay?
Yeah.
Okay. Bye-bye for today.
Bye.